In this video, we're going to talk about how to find bases for the null space of a matrix and for the column space of a matrix. So I want to do an example right away. So let's let A be this matrix. It's got 3 columns. Just to refer to them a little bit more easily, I'll refer to the columns as A1, A2, and A3. And this is row equivalent to the following matrix. So in this row reduced form, I'm going to refer to the columns as B1, B2, and B3. Okay, so let's find a basis for the null space and a basis for the column space. So for the null space, well, we know how to find the null space because we've talked about that a bunch. We use this row reduced form, and this is a coefficient matrix. So I would write down the equation for each row. So that's what this first line is. And then I isolate for the pivot variables. So there's a pivot in the first column and the second column, and that's where we're isolating for the x1 and the x2. And then from there, we can write down our answer in parametric vector form. And that's what we have here. So it turns out that when we solve for the null space, when we're solving the homogeneous equation ax equals 0, solving that in parametric vector form, always yields a basis for the null space. So the vectors that sort of pop out of this, they're definitely going to span the null space, because the way this is written, this is talking about all linear combinations of these vectors. And these vectors that sort of pop out, in front of these free variables, they're going to be linearly independent. And we commented on that in the previous section about why they're linearly independent. So at this point, we're actually ready to write down a basis. So the basis for my null space is, in this case, it's just one vector. -2, -1, 1. The basis for the null space, maybe I should say basis for the null space, is just this vector right here. In general, they'll be the vectors that are sort of attached to these free variables when I write down my answer in parametric vector form to the equation ax equals 0. Okay, so next let's talk about a basis for the column space. So for the column space, I actually need to make an observation first. So one observation that I want to make is, if I look at my two matrices, both the original and the row reduced form, notice that in the row reduced form, that when I look at the third column, B3, that's a linear combination of the other two. And I think pretty quickly see what the linear combination is. It's 2 times the first column plus the second column. That's how I'm going to get 2, 1, 0. If we look at the columns in the original matrix, it turns out the same linear dependence relation is satisfied. The third column is still 2 times the first column. Oops. Sorry, I just got shifted over. Let's shift it back. A3 is still 2 times the first column plus the second column. I'd encourage you guys to check that about the first 3 columns, about the 3 columns of the original matrix. So this is true in general. If there's, a linear dependence relation like I had here in my row reduced form, that same linear dependence relation is going to be true in the original. And that's going to be the key observation that's going to let us find a basis for the column space. So this is the observation that I sort of just mentioned. I want to write that down. So row operations preserve what are called linear dependence relationships of the columns. But what might happen is when we are doing those row operations, we might have changed the span of the columns. And I can actually see that in this example. If I were to look at the span of the columns in the row reduced form, notice that all the third entries are 0. So if I were to take any linear combination of the B's, the third entry would definitely be 0. But if I were to take a linear combination of any of the A vectors, it's possible for the third entry to be non-zero. So the span of the original columns and the span of these row reduced columns can definitely be different. So that's what this observation is stating. So the next thing that I sort of want to point out is, I got to go up to my example again, is based off of what we talked about in the last video with the spanning set theorem. When there is a vector like this, that can be written as a linear combination of the other ones, or even the A3, we can toss it out without changing the span. So notice that the vectors that I can toss out are the ones in the columns where I have a free variable, the columns that don't have pivots. Like I could toss out this third column. So it turns out that if I want a basis for my column space, what I look for is the pivot columns. The pivot columns of A, and it's really important that I'm talking about the original matrix right here, because when I do row operations, the span of the columns might change. So I have to be sure to go back to my original matrix and take the pivot columns in that original matrix when I'm looking for the basis for the column space. Okay, so in this problem right here, I just got to write down the pivot columns in the original matrix. So I know I have a pivot in the first and the second column, but I got to take the first and the second columns in the original matrix. So let's just write those down. And those are going to be a basis for the column space. So basis for column space of A is, so it's a set, and I had two pivot columns. So they were 1, 0, -4, and -2, 1, 5. Okay, so remember we talked a little bit about dimension earlier in a previous video of this section. Remember, dimension is how many vectors we have in the basis. So the dimension of my column space is 2. For the null space, there was one vector in this basis. So the dimension of the null space was 1. So I mentioned before that we're going to see dimension, this term, more in detail in section 4.5 and also in 4.6. In 4.6, we're going to learn a key fact about the null space and the column space and how their dimensions are related. It turns out that the dimension of the null space added to the dimension of the column space will always be equal to the number of columns in my matrix. I'd encourage you guys to think about why. We actually have enough information to answer this right now. I'd encourage you guys to pause the video for about 30 to 60 seconds, so 1 minute, let's say, and think about why this is. So 4, 3, 2, 1, pause the video. Pause the video and think about this for about 1 minute. Okay, so hopefully you guys did that. Hopefully you guys paused the video and thought about it. So again, I'll mention this more in 4.6, but the dimension of the null space, it'll turn out, is always the number of free variables. And the dimension of the column space is always going to be the number of pivots. So when I add up the number of free variables to the number of pivots, well, that'll always be the number of columns of A. So that's why this result is true.